Hello and welcome, honors students, and happy Friday. We have made it to the end of another week of virtual lessons. So today we're going to actually wrap up the last part of 14.4. Chapter 14 will be completely done. I did post your study guide. It is in Moodle for you to begin to look at. On Monday, I will have a virtual lesson and we will go through that study guide as a group. So today we're going to start talking about Graham's law. So we talked about Dalton's law of partial pressure and realizing that if you have a mixture of gas, that the total pressure is made up of the sum of all the partial pressures. And we looked at some example problems on that. So let's talk about Graham's law now. So Graham's law, how does the molar mass of a gas affect the rate at which the gas diffuses or effuses? So let's talk about that. So if you open a bottle, and this is pretty much straightforward material here. If you open up a bottle of perfume or you take an aerosol spray can of some fragrance and you make a spray, just put one spray out there. It doesn't matter where you are in the room, at some point, you are going to be able to smell that perfume or that fragrance, because the natural flow is to go from high concentration out to low concentration. Next year in biology, you're going to be learning a lot about this, and the concentration gradient does not take energy. You move a substance from areas of high concentration to low concentration by the gradient, and that is the same principle that this is working by. So it just moves. It's a gas, so it moves constantly, rapidly, and randomly in all directions, and that is diffusion. So the molecules in the perfume evaporate and diffuse or spread out through the entire room, and that is how you would be able to smell that, and so that's the principle of diffusion. So let's define diffusion. So please, in your notes, make sure you get this down. So this is an important term right here. So diffusion is a tendency of molecules to move towards area of lower concentrations until the concentration is uniform throughout. So it's going to go from high concentration to low concentration. Those are brackets. We're going to be talking about that upcoming here in the next chapter. So that's a concentration. So high concentration to low concentration, and that is what and how diffusion works. So diffusion is a tendency of molecules to move towards areas of low concentration. So here's an example. So you have this bromine. Now bromine is a liquid, and you have it in this container right here. In its normal state, it's liquid. Here they say it's in its vapor state. So in the vapor state, it is just going to diffuse throughout. So you're going to see what's happened here. You see it moving up. You can see the top part here is still a little light right there. It hasn't diffused completely throughout it. And then you get to here several hours later, the fumes are everywhere. And that is the principle of diffusion. So what is effusion? So effusion is the escape of a gas through tiny holes, or we could say pores. So if we were in the classroom, I had a really good demonstration that I was going to do on this. I was going to take a Ziploc bag, and I was going to show you the container that it came in, Ziploc, the world's best bags. And I was going to put some water in that bag. And I was going to take a beaker and have iodine solution in that beaker. And I was going to ask you, do you think that the iodine is going to get into this Ziploc bag? It is the best bag there is. I would ask you that question. And you would have probably said no. And I would have proved to you that that iodine will go into that bag. How could it go in that bag? Well, because it has these tiny holes. They're not actually called holes, they're pores. So these little pores can allow small molecules to go through, and iodine is a small molecule, and it actually would have gone into that bag. And when I pull the bag out of the solution, you would have noticed that the clear water that was in that Ziploc bag would now be this murkyish brownish color, which would be the iodine infused into it through the process of effusion to move through the pores. So we're not talking about a liquid here, we're talking about gas, but gas does the exact same thing. So diffusion is spreading out from high to low, and effusion is the escape of a gas through these pores. So with effusion and diffusion, the type of particle is important. It does matter. The size matters here. And if you have a small versus a large molecule, and we're going to talk about that, gases of lower molar mass diffuse and effuse faster than gases of high molar mass. So think about why this is. Well, let's talk about kinetic energy. Let's talk about kinetic energy. And you don't have to write this formula down. I'm not going to have you memorize this formula right here, but this is a good formula just for me for a talking point. So kinetic energy. And you talk about how fast it's moving. You see that it has everything to do here with the mass. If you have two molecules that have the same kinetic energy, the one with the smaller mass, if the mass was smaller, would it make sense that the velocity would have to be faster to have the same kinetic energy? So if it had a larger mass, in order to be the same kinetic energy, velocity would have to be lower. So hopefully that makes sense to you. You don't have to memorize this. I'm not going to have a problem to solve on this test for you, but the concept is important. So the smaller the molar mass of this molecule, and it has the same kinetic energy as another molecule, the smaller one will go faster. That way it has the same kinetic energy. So Graham's law of effusion. Let's get this down. This is important as well. Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. So one thing that I am not going to do is I'm not going to have us do Graham's law problems on this particular upcoming test. If we were in the classroom, I would have these are dealing with square roots. And I'm not sure how much you have used that, so I think it is a little bit more difficult to teach in a virtual setting than in person, so I'm going to leave the calculations off, but you do need to know the concept. So Graham's law of effusion states the rate of effusion of a gas is inversely proportional to the square root of the molar mass of that gas. So this law can also be applied to the diffusion of gases. If two objects with different masses have the same kinetic energy, the lighter object must be moving faster, and that's what I said. So if you look at what I had just talked about, kinetic energy equals 1/2 mass velocity squared. If you have two objects or two different gases with the same kinetic energy and they have molar mass differences, that means the smaller molar mass velocity must be faster in order for it to have the same kinetic energy. So let's think about this. Why do balloons filled with helium deflate faster than balloons filled with air? Think about that. So if you had a periodic table, which I have one right here, and you look at air, air is going to be somewhere in the neighborhood of about, because there's some gas, air, you're going to talk about 28 to 29 grams per mole. I'm going to go per mole. If you talk about helium, it is 4.00 grams per mole. So it's much smaller, so it is going to go faster through those pores, because even if it is the same temperature, the smaller would have to go faster. The velocity would have to be higher in order to have the same kinetic energy. So because this is smaller right here, it's going to escape the fastest. And that's probably what you notice if you have balloons for a birthday party or something like that. Those helium balloons go down pretty quickly. And that's what this is talking about right here. All right, so comparing effusion rates. Suppose you have two balloons, one filled with helium and the other filled with air. If the balloons are the same temperature, the particles in each balloon have the same average kinetic energy. But helium is so much less massive than oxygen or nitrogen molecules. So the molecules in air move more slowly than helium with the same kinetic energy. And that formula that I showed you, kinetic energy equals 1/2 mass velocity squared, proves that. Here is Graham's law of diffusion, and I'm not going to have you use this formula, so I'm going to just pass this one by pretty quick. Takes a little bit of practice to use this, and we don't have that particular method in that I can answer a lot of questions in the square root portion of this, so we're going to leave this one off the test. So I'm just going to pass through these here real quick. I'm not going to waste a lot of time on that. So let's look at a couple of key concepts here. So which gas below would effuse the fastest through a sealed latex balloon? So you have, say, 1, 2, 3, 4, 5 balloons filled up, and you have them all at 25 degrees Celsius, and you want to see which one would effuse and deflate the fastest. So what you'd have to do is look at the molar mass. So when you look at this, we know oxygen is going to equal 32, basically 0.00 grams per mole. Argon is equals 39.95 grams per mole. Nitrogen, dinitrogen monoxide is 16, 26, 27, 28 equals 28.01 grams per mole. So right now that's the smallest mass. Neon, let's look at neon. Oh, wait, we got one right here a little lower. So now we have 20.18 grams per mole. And then carbon monoxide, we have carbon at 12.01, so 16, 26, 28, 28.01 grams per mole. So when we come back up here, this is not 28.06, 28.02 is the nitrogen. Then you have to add the oxygen. So 2838, so 40.02 grams per mole. Sorry about that, a little mix up on that one. All right, so now simply put, when you have a question like this, you just have to look at which one is the smallest mass. Is at the same temperature. I stated that they're all at 25 degrees Celsius. So when I look at this, the smallest is right here. It's neon. So neon, a neon-filled balloon, it will effuse the fastest, and it'll deflate the quickest out of all those listed right there. So hopefully that makes sense to you. Here's a checkpoint question. So which of the following gas particles will diffuse fastest if all of these gases are at the same temperature and pressure? So once again, this is all about the molar mass when you look at these right here. You can look at D right away and say, what is happening there? That is a metal. It is in a liquid state. So we'll just cross that one off. That's not even going to be in contention here. So here we have, we'll just do some roundabout numbers of this one. So 35 and 35. So here we have roughly about 70 grams per mole. SO2 we have 32 and 42, 52, 62, 64. So we have about 64.06 grams per mole. And then here we have 28, 38, 44. Basically 44 grams per mole. So you should have pick C on that. It's the smallest one, and that is the correct response. So ladies and gentlemen, that actually finishes up this particular entire chapter, actually, where we learned a lot about gas. We learned about Boyle's law, Charles' law, Gay-Lussac's law, the combined gas law, the ideal gas law. We learned about ideal gases. We learned about diffusion, and now we learned about effusion. So once again, your study guide is posted for you. So in this section here, we looked at Dalton's law, we looked at Graham's law. We have few definitions: partial pressure, Dalton's law, partial pressure diffusion, effusion, and Graham's law of effusion. And that is the end of this particular chapter, ladies and gentlemen. So please do take a look at the assignment I have for 14.4. There's a few questions I did omit. They're using the square root formula, so I did take that one off of the homework, and you have your study guide for you. So thank you for watching. I hope you have a great weekend, and on Monday we will go through our study guide together for our upcoming test. Thank you. Go in peace.